Hey there, guys. Welcome back. Could you make sure you're commenting your names? Because at the moment I've got 5 of you present, which is not great. So make sure if you're here you comment your name so I can tick you off as attending. Cool. Right. So today we are looking at using the normal distribution to approximate a binomial distribution, which is quite good. I like this lecture. I think it's an interesting topic. It links together both your distributions from first year and from second year, so you get a bit of revision in there as well, which is useful. Cool. So, if we think about a binomial distribution first of all, it's a nice rough one. If we say that is x is a binomial with n number of trials and p probability of success. Obviously this is a discrete variable. And yeah, there we go. So the difference between that and a normal distribution is that a normal distribution is a continuous variable. So we can only actually do this. We're going to try and use one of these to approximate one of these. And you can kind of see the shapes almost there. I've purposely drawn one that wasn't completely symmetrical. But yeah, so the shape is almost the same. The big difference is this one is continuous and this one is discrete. And that's going to affect when we can do this. So we can only use a normal to approximate a binomial if there are lots and lots of trials. Because you can imagine the more trials we have, the closer a discrete distribution is going to look like a continuous distribution. And it's quite useful because if you've got lots and lots of trials, then the binomial distribution is actually quite hard to calculate, or at least it was quite hard to calculate back in the days where they used the statistics tables. If you guys calculate it, probably do it, no problem either way. But it can be useful to use a normal approximation anyway. So, for example, if we had a binomial like this, and let's say the binomial has 50 trials, I'm not drawing them all, and 0.48 probabilities of success. We can approximate that with a normal distribution with mu is 24, sigma is 12.48. That's what we're going to be doing today, working out how we can use this normal to approximate this binomial. Cool. Hey, Joseph, just got you there. Anybody else? I've still only got 8 of you ticked off, despite there's 13 of you watching. So if you are there, please write your name so I can tick you off on the register. Cool. All right. So you can only do this, as I said already, if n is large. And p is close to 0.5. Dan, why are you watching it twice? That's weird. How are you watching it twice? I won't question it, but maybe you'll learn twice as much. Okay, so yeah, if n is large and p is close to 0.5, we can do this. The reason p needs to be close to 0.5 is if you imagine your probability of success, your most likely binomial outcome will be P times N. Oh, nice. Cool. That's a good setup. Yeah, so your most likely outcome on a binomial is probability times the number of trials. So if I was rolling a dice if I was rolling a dice 60 times, the probability, so n is 60, the probability of rolling a 6, roll a 6 is 1/6. What's the most likely outcome? Well, the most likely outcome is I'm going to get 10 sixes. So if your probability, so that would be no good, because obviously out of 60, 10's over here. That's not a very symmetrical distribution. If my probability of rolling a 6, if my dice was biased, if my probability of rolling a 6 was actually 0.5, well, then my distribution would look like this. I'd have 30 in the middle, and it would peter off each way symmetrically. That would be a good candidate for a normal distribution. So for this to work, you have to have lots and lots of trials, and your probabilities of success needs to be pretty close to 0.5. Probably get away with it, maybe 0.4 to 0.6. It'd be slightly skewed and slightly less accurate, but your probability needs to be about 0.5. Okay then, so yeah, and that's because it needs to be symmetrical. Needs to be symmetrical. And n is large because it needs to come close to a continuous variable. Cool, everyone right so far with the idea, with the concept? We're going to fit a normal to use it as a binomial. I think the lag's like 2 seconds today, so you should be able to respond pretty quickly. All right, because I'm still only on 8 of you in attendance. Anybody watching this later, could you email me to let me know that you've watched the whole video? And then I will update your attendance, because I know college isn't meant to start till Wednesday this week. But in future it needs to be then and there, or you'll be marked as late. Cool. Right. So the way we're going to do this, the way we're going to turn one of these into one of these is we're going to find a relationship between n and p and mu and sigma. Now mu's nice and easy, because mu, the mean, is the middle number, and the middle number, if it's symmetrical, should just be given as we were just working out, n times p. So if you do your probability times your number of trials, the number you get, that's your mean. Standard deviation is a bit less obvious, so we get sigma is the square root of np times 1 minus p. I can't really give you a reason for that. You just need to learn this one. All that's doing really is matching up the spread of your normal with how quickly the spread of the binomial diminishes. So that's why we got 1 minus p, and it's why you got the mean times kind of diminishing and then square root. So it makes sense, but it's not as intuitive as this one, as the mean is. Cool, so we're going to use these equations, and we can then turn one of these into one of these. That's pretty much it. It's not much more difficult than that. There are a couple of things we've got to be aware of, but we will get to those shortly. So I've written the equations up here again. I would like you guys to try this. So I want you to first write the binomial model, explain why it can be approximated with a normal distribution, normal model, and then find out what mu and sigma will be in our normal distribution. So if I give you guys we've got quite a lot of time today. I think I'll give you 3 or 4 minutes to do that. If you could comment your answers when you've worked them all out. So yeah, let's give you, I think 3 minutes will be fair. So 3 minutes. Give it a go. Comment your answers. Cool. Looks good, Dan. Yeah, sounds good to me. We'll be going through it in about 15 seconds, but good, good, good. Cool. Yeah, Regan got it as well. Excellent. Both of you guys, excellent work. Excellent work so far. Good. All right. So yeah, writing the binomial model, nice and simple. We're just gonna do the old x wiggly line b 100 and 0.53. It's very slightly biased, that coin. It's almost not worth it. Explain why x can be approximated using a binomial, using a normal distribution. That's right, Frank. Tune in for now. I will tick you off as attending. Try and join in time next time, but fine for today. There you go. Yeah, so we want to. Why can we approximate it normally? I don't think anyone wrote any answers for this, so if you guys could explain to Frank why we can use a normal distribution to approximate this binomial distribution. Any ideas? Close to 0.5. Yeah, so the probability is close to 0.5. So that means that the data is symmetrical, as Dan said there. And what's the other reason? So that covers the probability. What's the other aspect that we need to include? N is large. So throwing a coin 100 times, that's enough data points, enough trials to be a bit closer to a continuous distribution. Nice and good answers there from you guys. Thank you, everybody. Cool. All right. Part C then. Find mu and find sigma. So mu is just going to be n times p. So mu equals 0.53 times 100, which you can do in your head and get mu is 53. Sigma is going to be the square root of 53 times 1 minus 0.53. And if you work that out, we get sigma is 4.99. Cool. So pretty straightforward. It's what we do with that that gets slightly more complicated. Okay, so good. Moving on then. There is a slight caveat. The reason why in this question we haven't actually done anything with the normal distribution yet is because there's something that we have to be careful of first. So we have to do something called a continuity correction. And I'll show you why we have to do this and what it means. So imagine we've got a binomial distribution. Obviously this doesn't have enough trials, but I can't be bothered to draw something that does. And we fit our normal distribution to this. Okay, let's say I wanted to find the probability x was less than or equal to 3. So with binomial, that would be quite easy. Less than or equal to 3, you would then shade in the bars you wanted. 3, 2, 1, 0. And you would find all of that probability. With the normal distribution, however, normal distribution isn't discrete. So if we did less than 3 on the normal distribution, what we'd actually find would be this area. Because it wouldn't know that we started with a discrete distribution. So that's not going to work. We'll lose a chunk of probability and we don't want that to happen. So what we're going to do instead is we need to do a continuity correction, which is a correction to correct for the fact we're using a continuous variable instead of a discrete variable. So our corrected to, we're going to go the probability x is less than this value, and that value there is 3.5. And we do that because otherwise we won't include the whole of this green bar. We want to include this. This is what we wanted on the discrete distribution. So to include that on a normal distribution, we need to go from 3.5 down. Right, does that make sense to everybody? Correct to that as we want to include all of 3. Cool. So that's the easiest one to spot. There's 2 more corrections that we have to do as well, though. So I'd like you guys to have a think about this and to comment what you think the answers are. So let's draw another distribution quickly. And we'll have 17, 18, 19, 20. I want to find the probability x is more than 18. This is our binomial question. What am I going to turn that into? So could you guys try and work out what it needs to be and then type your answer. I'll give you 30 seconds to try and think of what that's going to turn into, starting from now. Cool, Isaac. You've gone 17.5. Do we want to include 18 though? So our binomial question was greater than 18, so we don't want to include the 18 bar. So none of this is included. If I shade in the bits we want 19, 20, 21, 22. So would you care to revise your answer? Any ideas? Yep, 18.5. Nice. Thank you, Sam, as well. Good. So yeah, that needs to be 18.5. Because otherwise, we're going to include 18. We don't want that because we wanted it to be greater than 18. So I would always sketch these. If you do a sketch, you shade it in. You don't really have to worry about it. You can just look at the graph and see what you need to get. All right, one more. This one's going to be a little bit harder. So we'll have 7, 8, 9, 10. So this time I want to try and find the probability x equals 7. How would I do this on a normal distribution? So another 30 seconds, have a think, see if you guys can come up with the right answer. Also, don't forget to comment your name. I know there's 14 of you now, and I definitely don't have 14 people on my register. So please put a comment. Cool, that was a bit quick maybe. Dan, you've gone for 6.5 to 7.5. Yeah, that looks good to me. So let's shade it and work it out. So we want 7. Of course, if we just type 7 into a normal distribution, we get 0 because it's continuous. So to include all of this bar, we need to go from 6.5 to 7.5. So on the normal distribution, we're going to type in probability 6.5 less than x less than 7.5. And if we've found mu and sigma correctly, if we've done the continuity correction, we should get a pretty good approximation to the normal probability. So let's put those two ideas together and see if it works. So just to summarize this then, if you've got probability x is less than or equal to a, you need to use probability x is less than a plus 0.5. The probability x is more than a, use probability x is more than a minus 0.5. For probability x equals a, use probability a minus 0.5 x a plus 0.5. Cool, and there's a couple others in there as well. You could also have greater than or equal to a, in which case you'd want to include a, so you'd go a minus 0.5. Yeah, you could go down and include it as well, and same here. So always sketch it is the safe way of doing these. So let's put that as well. Always sketch. Cool. All right. Why only equal to on the top inequality? I just felt like putting equal to there. If I wanted to do the other kind of possibilities, we could have to think about those as well. If we want to do probability x is less than a, there's a, we want less than a, we'd go probability x is less than a, take 0.5. And if we wanted to do probability x is greater than or equal to a, we do probability x is greater than a minus 0.5. Is that right? No, sorry, this should be a plus. Change that. Yeah, so I would always sketch it. If you've always sketched it, you can see whether you need to include a, and if you need to include a, you need to go 0.5 below it. If you don't want to include a, like over here, you want to go either above or below it. So always do a sketch to tell if you need to include the value. If you need to include it, depending which way around your sign is, you're going to need to add or subtract 0.5. I only did a couple examples just now because therefore you guys would always sketch anyway. So sketch it, check whether it's less than or more than, check if you need to include, taking away or plussing 0.5 either side of the value you want. All right, let's try this then. So, particular type of flower bulb will 55% will choose yellow flowers. A random sample of 80 bulbs is planted. Calculate the percentage error incurred when using a normal approximation to estimate the probability there are exactly 50 yellow flowers. There's quite a lot going on there. We're going to do a binomial distribution, a normal distribution, and find the percentage error for both. So you're going to need some equations. We've got then mu equals np, sigma equals root, and also percentage error equals estimate, take actual over actual times 100. So if you guys give this a go, I'm going to give you 5 minutes to do this one. Comment if you get stuck and I will give you some hints. Cool, thank you. I think it should be closer to 0.82%. So have a check through, Oliver. You might have made a mistake somewhere. Cool. Right. Hopefully you guys are close to getting answers. We'll slowly go through it then. So I can clear some space. All right. So we'll start with the standard binomial distribution, and I'll bring up the old calculator. There we go. So I'm going to lose your comments now. There we go. Cool. All right. So first of all, x is a binomial with 80 and 0.55. We want the probability x equals 50. So let's do that on the calculator. Statistics, distribution, binomial, BPD, because we've got something equals data, x is 50, number of trials 80, probability success 0.55. Cool. Execute, and we get probability is 0.356. Cool. Okay, so now we need to do the normal. So to do the normal calculations, first we need to work out n, mu, and sigma. So mu is going to be 80 times 0.55, which I work out to be 44. And sigma is going to be square root 44 times 1 minus 0.55, which I work out to be 4.45. Dan 0.92, I made it 0.82, so have a check over that. So I can write my distribution. X is a normal with a mean of 44, a standard deviation of 4.45 squared. Let's get rid of the calculator for a sec. There you go. So there's a distribution. So we're going to type in, we need to do a continuity correction. So we want the probability x is 50. So we're going to do a quick sketch. There's 50, 51, 49. We're going to need to go from 50.5 to 49.5, as you can see there. So 49.5 to 50.5. Cool. Right, so I'll bring the calculator back up and we will work this one out. So there we are. And we're looking for normal. And CD because we're cumulative. The lower is going to be 49.5. Upper 50.5. Sigma was 4.45. And mu was 44. Cool. So if we draw it, see there's a little strip for 50, and I get 0.36, round that up to 2. Cool. So those are my two probabilities. My p equals should be 0.0. Yeah, I've missed out 0 in both cases. At least I was consistent. Uh, Fixed that. Thank you for the comments there, guys. Cool, 0.0356 and 0.0362. So if I want to work out the percentage error, I'm just going to subtract, well, which one's our estimate? It would be the normal approximation. So it doesn't really matter which way we subtract them. 0.0362, take 0.0356 divided by the actual 0.0356 times 100, and I make it out to be 0.82%. Cool. Has anyone got any questions? So I know a few of you had different answers. Have I missed another 0? Whoever missed a 0. Oh no, I think that's the 0 I previously missed. So yeah, anyone got any questions about that one? I'm going to assume that we're good. If no one else is commenting, cool. Right, so you guys are going to try another one. We'll see how this one goes. So same idea, exactly the same steps. Could you guys try? Oh, I can't copy numbers. Ah, fine. Yeah, neither can I. Neither can I, Dan. It's a common mistake with mathematicians. Cool. All right. It's 0.0365 on normal, is it? Binomial. 356, 365. It is. It is. Sorry. God, copying awfully today. 365. There we go. So that needs to be changed down here as well. The answer's right though, because my workings are correct, just not the ones that matter, not the ones in front of you guys. 365, 365. Oh well, maybe I'll get it better tomorrow. Yeah, it is me. Cool. The answer is still the same though. I did it right in my workings here, so yeah, cool. All right, on to the next slide if you're all okay with that, and I haven't made any more copying errors. No. Cool. Right, moving on. So, a drill bit manufacturer has a oh, let's move this down. A drill bit manufacturer claims that 52% of its bits last longer than 40 hours. A random sample of 30 bits is taken, and X bits last longer than 40 hours. Find the probability X is less than 17, and then a second sample is taken. Use a suitable approximation. Whenever it says that, use a suitable approximation, it means use normal. So you've got a binomial question to start with, and then a normal bit for the second part of this question. Could you guys give it a go? How long have we got today? Quite a while. Let's go 8 minutes for that. Please comment if you get stuck though. I'd rather you say stuff than just sit there and wait. It's always better if you guys give the questions a go as well. Cool. 8 minutes starting from now. Yeah, the class width can only do less than or equal to. So you'll need to sketch your binomial and work out how to do it on the class width. It's doable, but you will need to be a bit more careful with it. Class width only ever does less than or equal to, and on the yeah, part A, Regan. I don't know actually. I haven't done this. I'll do it now. Ooh, two different answers to part A. I make it 0.6277. Regan, check if you. I think you might have used 17, but class whiz calculators do less than or equal to, so you've actually done less than or equal to 17. So you probably want to use 16 for part A. 16 for part A. Still noticing there's 13 of you in the chat, even if 2 of you are, Dan, that still leaves, well, that should be 12 of you. So 4 of you haven't got your attendance sorted yet, so please let me know. And just to check that everyone's watched this, could you all send me an email with the number 42 in it, just so I can check that everyone who was here at the beginning is still here at this point in the video. So send me 42 to my email, just as an extra check for attendance. And if you are watching this after the fact, send me 42 anyway, and then I know that you have watched this video. And we'll do random little checks like that every so often in different videos, just so I know that you guys have attended properly. Thanks, Ollie. Sweet, lots of nice emails coming in from you guys. Like that was quick. Ooh. Anyone else need any help for part B? So part B, best advice is to sketch it. Sketching is the most important thing. What did you do, Dan? I suppose I should do part B as well then. I made the same mistake then. That was good. So that's all going to be wrong. Oh, and we got time up. Okay, do we use the binomial approximation part B? Well, it's a normal approximation to a binomial, Isaac. So yeah, you're using a normal distribution, but you need to find the mean, and to find the mean, you're using the binomial distribution. So both really. All right, let's go through part A. If you guys are still working on part B, that's fine. I'll give you a bit more time to do it. So part A then, we've got x is a binomial with n is 30 and p is 0.52. We're trying to work out x is less than 17. So on the class whiz, you need to do x is less than or equal to 16. We can just do it on the graphical though. So let's do that. Distribution, binomial distribution, BCD. And my lower value is going to be 0. Upper value is going to be 16. Number of trials 30. Probability 0.52. And as you guys saw, the answer 0.6277. There you go. Cool. So well done on the first bit. Second bit then. A little bit more involved. So we've now got x as a binomial with 600 and 0.52. And we want to find the probability x is between 300 and 350. So we need to turn this into a normal distribution. So I'm going to get rid of my workings from before. Okay, so mu is going to be 600 times 0.52. Can't hear me 42. Yeah, that's fine, Dan. Do it later. No worries. I know you're here. I can see you talking anyway. So we get 312. Sigma is the square root of 312 times 1 minus 0.52, which should be 12.23 or 12.24 to 2 decimal places. Cool. Yeah, Sam, it looks like your upper and lower are not quite right there. So those are our two bits for our distributions. X is a normal with mean 312, sigma 12.24 squared. But we need to do a continuity correction. So my correction, if you think about it, if I draw it up here, can you guys see that? It's not great, is it? Tell you what, let's just get rid of this picture now. Maybe not. You can see that, it's fine. Cool. So we want it between, if we call this one 350 or 300 and this one 350, we want to include all of the 300 bar. So we want to include all of this. So to do that, we need to go from 299.5 and then for the upper bar, we want to, oh wait, hang on. Between 300 and 500. Ooh, actually, maybe that's... Just wondering whether to include these or not. I think we do want to include both, yeah. So I think 299.5 for this one, and for this one it's going to be 350.5 because we want to include all of that bar, and everything in the middle. So we're going to go to x and then 300.5. There we go. So, yes, Ollie, I do agree with what you said in the chat. Good. So we're going to work out that with our calculator. So if I type everything in, distribution, normal distribution, NCD, lower 299.5, upper 350.5, mu 12.24, and sigma 312. We can draw it again, and there is our answer. So 0.846 or 8456. Yeah, cool. All right. Isn't including stuff outside the bounds in the question? How do you mean, Isaac? Let's have a look at that. Isn't it then including stuff outside the bounds? No, because we want to include the number 300 and we want to include the number 350. So yeah, we do want to go 299.5, 300.5. Cool. Anybody else got any questions or bits they want to ask about that? It's really annoying how something division is about you on the calculator that keeps catching me up. Standard deviation is above mu. Yeah. I do that all the time. Yeah, just get in the habit of it. You will get to it. I mean, I was making the same mistake last week, and I've taught 3 times as many lectures as you guys have been in. So when you've done, another 4 hours of practice of this, you'll have it. So don't worry too much. Yeah, cool. All right, moving on then. We're going to try another one. We're doing pretty well for time today. So question about breakfast cereal. Did you guys have toys in your breakfast cereal? You too old for that? Too young for that even? It was pretty good. Those were the glorious days of toys and breakfast. Anyway, so a particular breakfast cereal has 56%. 56% of its boxes have prizes inside. A random sample of 100 boxes is taken. Find the exact value of the probability that exactly 55 boxes contain a prize, and then find the percentage error when using the normal distribution. So again, give it a go. 5 marks. I'll give you 6 minutes to do it because I'm feeling kind. And because I think we're coming. Maybe I'll give you longer. Maybe let's say 7 minutes. Don't forget to sketch it and see if you can find these probabilities. Cool. Give it a go. What do we do about the fact it says exact value? I didn't spot that either. Don't use a calculator. Put down a calculator and do it using the binomial expansion method. We definitely went through it last week. The way that doesn't involve calculators. Let me check that. That's an interesting question. Cool. Yeah, the book doesn't seem to care, so yeah, you can write it as exactly as you like, but you still get a decimal. So bad question, bad wording, perhaps. I think maybe they've said that to distinguish between that answer and that part B is an approximation, so that they're telling you this is the real answer, part B is the approximation. That's all I can work out because you wouldn't be able to do that. Exactly. I don't see how you could do 0.56 to the power 55 in your heads, so don't worry too much about that bit. Cool. Right. Part A, Isaac. Yeah, you're very close. I made it. I got point 784. Let's have a go. We'll go through this. Cool. Unless you guys want a bit longer. Haven't seen any final answers yet. Nah, let's do it. Okie dokie. So we've got binomial for part A, x, b, 100, 5, 6. Seeing as we talked about it, let's do this without a or let's do the workings without a calculator. So we get 100 C55, 0.56 to the power 55, 0.44 to the power 45. And if you type that in, you get what was it? 0.0784. Cool. Okay, so that's the first one. Part B then, we need to find the normal distribution. So mu is going to be 100 times 5, 6, so 56. Sigma is going to be root 56 times 0.44, which I got as 4.96. So we can say x is a normal with 56 and 4.96 squared. Everyone right so far? So we've got our normal distribution. So we need to do a continuity correction. So we're going to say it's the probability x is less than 55.5, more than 54.5. Bring up the trusty graphical calculator. Cool. So we want a normal CD. And what are we talking about? 54.5, 55.5, 4.96, and 56. Cool. There we go. And I've got 0.0787. Cool. There we go. So those are two answers. Percentage error is going to be 0.0787 take 0.0784 divided by actual 0.0784 times 100. And I think you get 0.38% on that one. Yeah. Nicely done, Sam. Cool. Oliver, slightly out there, so just have a quick check. All right, has anybody got any questions about this? I got slightly out because I need more decimal places. Yeah, cool. They'll probably have a range of answers for these anyway. Can you use calculator for A? Yeah, I think you can. The only reason I didn't was because it says exact, and plus I wanted to do a bit of practice on that method so you guys have seen it, because there are some questions where you have to do it that way. Cool. Yeah, I think that might be it for today. Is there one more? No. All right. So that's all I planned. We went through that well fast. That normally takes me an hour and a half, but I guess we can be a bit quicker without without going around and helping. Um, so yeah, for today, I mean, you're not meant to have a lecture today anyway, so I'm gonna let you guys go early. Um, I would recommend you do a couple. You got 20 minutes now. I would recommend you do a couple of page 55 just for extra practice of this. We've done a nice selection, but I think there's 2 or 3 more on page 55 that'd be good.